Okay, so this is the last lesson for the quantities unit. And today we're going to calculate percent yield. So percent yield is a quantitative measure of how much product is produced based on how much should be produced. So one of the questions in the homework, we'll get you to read the section in the textbook, but now that we've started to analyze reactions analytically, then it's not enough just to say, oh, switch the partners, that this is what the product's going to be. There are situations where you want to know how much yield or how much product you got based on theoretically using stoichiometry predicting how much you should have made. So, if you're running a factory and you have a product, you want to make sure that your processes are efficient. So there is human error that can affect yield. There is also equipment error. So if we were doing a lab or you were doing a lab and there were plenty of places where you had to switch between apparatus, like pour something into a beaker, measure something out, and then pour it into something else, and then pour it into something else. At each of those stages, there could be material loss, just based on maybe it got stuck to the beaker, whatever. So yield can be affected by that. There are actually plenty of reactions that don't just go in what we call one step. So the reactants as written make the products as written. We'll talk next year about reaction mechanisms or reactions that take more than one step. We'll also look at reversible reactions. So once you start to make products, there are plenty of reactions that then those products start to collide, and then the reaction goes in the reverse direction and you actually start to reform the reactants. So that can also affect yield as well. So this is really just scratching the surface of this kind of thinking. Okay, so when you do a percentage, you always multiply by 100, right? And then when you have a paper and pencil task, the actual yield, so the yield that you actually get from an experiment, should always be smaller than the theoretical yield. So theoretical yield is how much should you get predicted by stoichiometry. So if everything was perfect, then what should you get? So when you do a lab, sometimes you can possibly get greater than 100% yield, which would mean then that you've been affected by probably contaminants, often something like water. So material may look dry, but it's not. And then maybe there's residual water that you don't want in your product, and that is affecting the yield. Things like that. But for paper and pencil tasks, you should definitely get below 100. So if you don't, then, especially in this case, because we obviously can't do labs, then you should definitely take a look again at your math. Okay, so actual yield, the amount of product obtained in the experiment. So again, on a paper and pencil task, you have to be given this. Okay, and then the theoretical yield, you're going to predict the product, the amount of the product made using stoichiometry. So we've already done the math for this. The actual yield calculation, that simple formula, is really worth like 2 marks. Like, it's really easy to do, but we have to get there. Okay, so we're going to predict how much product should be produced by stoich and then use the percent yield formula to compare it to what is actually produced. Okay, so since we've already basically done all this math except the final percentage step, we're just going to jump right into a question. Okay, so this is what a question would probably look like. First of all, you need to balance this equation, which it's not. And then it says if 50 grams of oxygen reacts, calculate the grams of carbon dioxide that can be produced. So we are going to use stoichiometry here. And then, so this is going to be the theoretical yield. Theoretically, how much should we get? And then if the actual yield was 35 grams, so again, you have to be given the actual yield. Sorry for my underline there. What was the percent yield of the experiment? So A is, if you are the kind of person who does not like to balance, A is going to be what I would call annoying. But then B will require the most math, and then C is really pretty straightforward. As long as you remember that actual yield, which one goes on the top of the fraction really, and which one goes at the bottom. But again, since you're going to get less than 100, then because this is just an example on paper and pencil, then you can definitely even think of it like that actual yield will always be smaller than theoretical yield, unless you're doing a for real lab and you have contamination. Okay, so this is a combustion reaction, and it is pretty, these coefficients are going to get pretty high. So maybe doing this kind of left side, right side chart might help you in this case. So we have 8 carbons and 1 carbon. We have 18 hydrogens and 2 on the other side. And then we have 2, and then we have 2 plus 1 on the product side for oxygen. Okay, so it can be tempting to try to put 9 in front of the water to make 18 hydrogens. However, the problem with that is if you put a 9, so don't do this, but if you put, I'm just going to read it up here. If you put a 9 in front of the water, that's going to make 9 oxygens. And there's no way to then make, to then balance the even number here on the reactant side, unless you use fractions, which you don't need to. And a lot of people, especially because we're going to use that coefficient later in the ratio, then that can really start to bother people. So in order to, if you want to make something doubled or even, then the easiest and the most reduced way to do that is to double it. So if we're going to double the 9, then you're going to get 18. So we actually want, we're going to actually have to double the 18 hydrogens on this side, which means we're going to put 18 on that side. And remember, you can always reduce at the end. So yes, these are big coefficients, but that's okay. You're going to see that it's all going to work out. So now we have an even number of oxygens, which, because the oxygen on the reactant side is by itself, is going to be the easiest one to balance. Okay, so let's deal with the carbons. So now I've put a 2 out front here, so that makes 16 carbons, 2 times 8, which means that we need a 16 over here. Okay, so the carbon and the hydrogen are balanced, and then we just need to figure out how many oxygens we have on the product side. So 16 times 2 is 32. Sorry, a little brain fart there. 32. Okay, and then 32 plus 18 is 50. So we actually have 50 oxygens. So then over here, because we already have a 2, you just do 50 divided by 2. Okay, so none of these numbers can be divided by anything to make them more reduced. So combustion reactions are the most annoying to balance, and they can have pretty large coefficients, and indicated by how many carbons we have here. And like I said, you can certainly do 25 over 2, but most people, that is not a requirement. And if you don't like fractions, then please don't feel like I expect you to do that. Okay, so we'll I'll continue on to do B and C on another page because I don't want to squish. Okay, so we have our balanced reaction. Now, if you guys wrote it out, then you can just keep going, but maybe now you need to rewrite it, which is fine. Because when we have these kinds of questions, again, I think it's easy to do what we've been doing the whole time. Mass, molar mass, and moles. So we're given 50 grams of oxygen. O2 is, its molecular weight is 2 times 16. So 32 grams per mole. And then moles, of course, is mass divided by molar mass, which is 1.56. Okay. And because in part C, it says the actual yield of carbon dioxide. So I could have given you the, yield of, the actual yield of water, but I didn't. I could have given you mass of octane as well, and you would have had to do limiting reagent, but that's not what this question asks. So there is a variety of things that you can do. Okay, so we're looking for the theoretical yield of carbon because we're given the actual yield and asked about percent yield. So again, we're given the actual yield of, what are we given? 35 grams. Okay, so our theoretical yield should be greater than 35. So if it's not, then you can, then you would get a number above 100, which isn't possible unless you're doing a real lab and you've got contaminants. Okay, so that's not what we have here, or on any question in the homework paper. If we were going to write it like the test or assignment, if there was an exam, it would never do that. Okay, so now we have oxygen's moles, and we want the grams of carbon dioxide, so we need to use STOIC to change it into the grams, the moles of carbon dioxide, which we can then change into the grams. So it's up to you if you want to wait and write down the molecular weight, or you want to do it now. It doesn't really matter. So how did I know that we need to go all the way to grams? When you do percentage, you have to have the same unit. So when you, the percent yield formula is actual yield over theoretical yield times 100, and percentage doesn't have a unit. So we want our units to cancel out. So could you be given moles? Yeah, you could do this with moles, no problem. But we were given our actual yield in grams, which means that we need our bottom number to be in grams so that they cancel out. And then you're left with the units of percent, like there's not really units for that. So when you get to this kind of question, then you know that you have to go all the way back to grams because the actual yield we were given, was 35. Okay, so we want our answer in grams and we want it to be higher. We want it to be bigger than 35. So it's up to you. So carbon is 12 and 2 oxygens is 32, which makes 44 grams per mole. So you can write it in there now, or you can wait till you're done. It doesn't really matter. So we need how many moles of CO2? Its coefficient is 16. We are using the 1.56 moles of oxygen, and its coefficient is 25. Okay, so again, decide how you're going to solve that, whether it's cross multiplying. You can do 1.56 divided by 25 and then times 16. You'll get the same answer. I'm just going to use 4 decimal places. Okay, so now I'm changing it into mass. If you're a triangle person, I'll write it down again. Okay. So now this, because we use stoichiometry to predict, then this is the theoretical yield. Okay, this is how much we should get. How much did we get? The actual yield? Oh, we got 35 grams, but no problem because that makes sense. We want the theoretical yield to be greater, because if it was in a perfect chemistry world, then we would get 100% yield. But for a variety of reasons, we're not going to, which means we are going to get less than 100. Okay, so that makes sense. So now, like I said, this part of it is much more math, and really none of this is new. All of this you've done before. We've done, changing into moles, this first step here, balancing, then doing the stoich, remembering that anytime you have to change the moles, always moles, of one thing into something else, then you have to use a stoich ratio to compare. And then this time we know we have to change it back into mass because we need the units to cancel out. And we were given our actual yield in grams. Okay? So I'm just going to make a new, see if I can get rid of that. Okay, so now we're going to do part C, which says if actual yield is 35 grams, what's percent yield? So percent yield is actual yield divided by theoretical yield times 100. So again, now we have grams, the grams cancel out. So our answer is going to be left as a percentage. So the new part to today, the actual yield, really is actually not that big of a deal. Okay, so more important that you can know how to change things into moles and how to do stoichiometry, or that would be worth the most marks. Okay, thank you. The homework is listed on D2L with the solutions from the textbook.